Good morning, students. I am Priya Sharma, EC Department, SIRT College, Bhopal. Sage Anandam. Today we are going to discuss about the topic Magnetron, which is a third topic of Unit 1. So basically, this will contents of this presentation or the lecture is introduction to magnetrons, then construction, working and its operations, performance characteristics, and lastly the applications. Coming to the introduction portion, the magnetrons are the cross-field tubes in which the electric and magnetic fields are perpendicular to each other. It is a diode, usually of cylindrical configuration with a thick cylindrical cathode at the center and a coaxial cylindrical block of copper as anode. In the anode block, there are a number of holes and slots which act as resonant cavities. The space between the anode and the cathode is the interaction space, and to one of the cavities is connected to a coaxial line or waveguide for extracting the output. It is a cross-field device as the electric field between the anode and the cathode is radial, whereas the magnetic field produced by a permanent magnet is axial. The permanent magnet is placed such that the magnetic lines are parallel to the vertical cathode and perpendicular to the electric field between the cathode and the anode. So the magnetrons are a vacuum tube which is used to generate microwaves at high powers, and its working principle, as I told you, is the interaction between electron beam and a magnetic field. So this is the basic diagram of a magnetron. It is 8-cavity magnetron. As you can see that there are 8 slots. So the center portion is the cathode, and then we have the anode in the slots. So the cathode is in the center of the chamber, or this is the cylinder. There are cylindrical cavities around the cathode, and these are open along their length and connect to the common cavity space. The output of the magnetron is drawn from any one of the cavities by a coaxial line or by using a waveguide. Like in this, we have taken output from here. Now coming to the working principle or the operation of the magnetrons, I have told you earlier that we have taken the 8 cavity that are tightly coupled to each other. An N cavity tightly coupled system will have N nodes of operations, each of which is uniquely characterized by a combination of frequency and phase of oscillation relatively to the adjacent cavity. Depending on the relative strength of the electric and the magnetic fields, the electrons released from the cavity move towards the anode will navigate through the interaction space. In the absence of the magnetic field, the electron travels straight from the cathode to the anode due to the radial electric field force acting on it. If the magnetic field strength is increased slightly, it will exert a lateral force bending the path of the electron. If the strength of the magnetic field is made sufficiently high so as to prevent the electrons from reaching the anode, the anode current becomes zero. The magnetic field required to return electrons back to the cathode just grazing the surface of the anode is called the critical magnetic field, which is also known as Hull's cutoff magnetic field, whose derivation or the equation is being used directly in the exams and the numericals are taken. So if the magnetic field is made larger than the critical field, the electron experiences a greater rotational force and may return back to the cathode quite faster. All such electrons may cause backheating of the cathode. This can be avoided by switching off the heater's supply after commencement of oscillation. This is done to avoid fall in the emitting efficiency of the cathode. So I have told you about the cutoff magnetic field, which is denoted by BC, or the Hull's magnetic field, whose formula is given by the magnetic field is equal to 1 upon small b root over 8 am v naught upon E. So if B magnetic field is greater than the cutoff magnetic field, it will experience a greater rotational force and return to the cathode quite faster. If electric field is greater than the magnetic field, the electrons reach at the anode, but the path will be bent because of the magnetic field. And if inverse is taken, the electrons return back to the cathode. So this is the basic operation which I have told you. High negative potential at cathode is created with a high voltage DC power. Cathode emits electrons. Path depends on the strength and direction of electric and magnetic fields. The magnetic field causes the electrons to get attracted towards the positive anode and starts to spiral in a circular path. Then they sweep past the openings of the cavities which are open along their lengths. Then these electrons include high frequency radio field in the cavity, due to which the electrons get bunched into the groups. Then this field goes into the output coupling loop, which in turn connected to the waveguide or antenna depending upon the output requirements. Coming to the performance characteristics of a magnetron, its frequency range lies between 500 megahertz to 12 gigahertz. The output power is in excess of 250 kilowatt if used in pulsed mode, 10 megawatt if used in ultra high frequency band at 2 milliwatt X band, and 8 kilowatt at 95 gigahertz. Efficiency lies between 40 to 70% and duty cycle is 0.1 circle. Now coming to the application portion of this magnetrons, its pulse radar is the single most important application with large pulse powers. Then voltage tunable magnetrons, known as VTMs, are used in sweep oscillators, in telemetry and in missile applications. Fixed frequency continuous wave magnetrons are used for industrial heating and microwave oven. That's all for today's magnetron topic. Thank you so much. Please like and share this video so that all the students who want this video, who want this material, can get through them and make them help in their examination. Thank you once again. All the best for your exams. Say Janandam.